So good evening one and all. So in your last class in mass spectrometry, we discussed about variable types of ions starting from molecular ion, then fragment ion, even electron ion, odd electron ion. After that we learn about what are isotopic ions. Okay, isotopic ions generally contributing peaks are m plus 1, m plus 2, etc. There generally we are get differentiated by m plus x. X is nothing but the difference between implicit value of a molecular ion followed by corresponding isotopic ion. Okay, later on we does a sample example only when one halogen element is present in a given molecule such as chlorine and bromine. So there we learn one selective formula, binomial expansion formula, a plus b to the power of n, to calculate isotopic peak intensities with respect to one halogen, 2, 3, etc. Okay, so for one halogen you may expect 1:3 peak, 2 halogens 9:2, 6:1, 3 halogens, 4 halogens, like that generally we discuss. Then later on 1 bromine, 2 bromine, 3 bromine, 1:1, 1:2, 2:1, 1:3, 3:1, like that. So later on mixed halogens, sulfur, etc. So everything we learn regarding isotopic peak, also with respect to corresponding multiple halogens and multiple isotopes. Okay, right. Next, after isotopic peak, next ion is multiply charged ion. Multiply charged ion, it is also called multiple charged ion. Two names are there. It may have a multiple charge, otherwise it may have more than one charge. That is called multiple charged ion. So you can write like this. See, the ion having more than one charge, if any ion having more than one charge, that is called multiple charged ion. Suppose if I take m plus, this is called unipositive ion. This is not multiple charged ion. Then you can write directly m plus plus, otherwise m plus plus plus, otherwise you can say m plus plus plus, like that. So these all are called multiply charged ion, also called multiple charged ion. So the positive charged ion having more than 1 plus 1 charge, or plus 2 plus 3, like that, there belongs to multiple charged ion. This is not a multiple charged ion. Okay, so this is multiply charged ion. So generally we will say multiple charge, but you can also say multiply charged ion. Okay, so generally here Z value may be changes. For unipositive ion, Z value is 1. For this one, what is Z value? 1. But what about this case? Here Z value is 2, or Z value may be 3, and Z value may be, it may be 4, or it may be n, etc. That depends upon the type of cation formed. So based on these charges, we need to divide with suitable number. So this kind of multiply charged ions are produced by, here you may expect a nitrogen heterocycle compounds, nitrogen heterocyclic compounds. So most of the nitrogen heterocyclic compounds can show this kind of character: pyridine, quinoline, isoquinoline, etc. Then we can also go through a selective polynuclear compounds, polynuclear aromatic compounds, polynuclear aromatic compounds such as naphthalene, anthracene, trypsin, etc. Next, we can also take one example of OMCs, and we can also take few examples of metals. Even pure metals, pure OMCs can also show this character. So this kind of functional groups can show a property of polycharged skeleton. Okay, so especially for this one, peak is intense. Peak will be similar to intense and normal peaks. Here it will be a sharp peak, is intense and sharp. Okay, similar to normal ion. These ions are similar to normal unipositive ion. So what it means? How unipositive ions are showing a sharp vertical line, similar to unipositive ion they are also showing. So there is no special difference between multiply charged ion and normal ions. Both are same only, but only thing is they carry more than one charge. That is the difference. Okay, so best example, if I take pyridine. So pyridine have a tendency to lose 2 electron. During electronic impact, they may lose 2 electron. If they lose 2 electron, what is the charge obtained on nitrogen? Nitrogen charge may be plus here. 2 electrons is removed. So we can say plus 2. So how to calculate M by Z value for this one? M by Z is equal to, now this is 79 by 2 I am writing. Why 79? 5 carbons, 1 nitrogen belongs to 79. Divide by 2. Okay. So finally you will get 39.5. So this value is not every time a non-integer. Sometimes it may be integer. So I can say that M by Z value for a multiply charged ion may be integer or may be non-integer. So but always peak will be sharp line only. Like this you will get the peak. Suppose for this one, if I take percentage of intensity, M by Z value, your peak intensity will be like this. And what about this value? This value is 39.5. So this is M by Z value. It may be always sharp only. You don't expect any broad peak. Broad possible only for metastable ion. But every ion in mass spectrometry that is appeared in the form of a short vertical line. Right? Take it. So your metals means you can take Grignard reagent and ferrocene. Ferrocene and your metals calcium, magnesium, etc. Quinoline, isoquinoline, pyridine, etc. Here naphthalene, anthracene, tyrosine, etc. Your examples are important. Which among the following will show multiply charged ion in mass spectrum? On that time you need to select the corresponding combination of a given element. Clear? Now see, especially for multiply charged ion, M by Z value may be integer or non-integer. It may be integer or it may be non-integer, which means it may be a fraction number, but peak is not broad peak, it is a sharp peak. These statements they are giving in GATE exam. Okay, multiply charged ion will show a broad intense peak, a sharp vertical peak, otherwise a sharp non-integer peak, a sharp integer peak, like that. So statements are giving. Remember, it may be a integer or non-integer, that depends upon the corresponding element or corresponding organic molecule. So that may give a vertical line, and it should be always sharp, and it should be intense, and your embedded value may be integer or non-integer. Sometimes you may get integer, sometimes it may be non-integer. Okay, so that's why it is integer or non-integer. Suppose if I take tyrosine, this is called tyrosine. After electronic impact, you will get these two. They may lose 2 electrons. Tyrosine. This is tyrosine, a polynuclear aromatic compound. Okay. So when they lose 2 electrons, and initially, if you remove 1 electron, then what about embedded value for this molecule? See, this is embedded value for all carbons. It may be 228 divided by how much? That is 2. Embedded. Polynuclear aromatic molecules, this number will be divided. Then total embedded value, every carbon 12, every hydrogen 1, if you count, you will get 228. And finally, peak is appeared at 114. So in mass spectrometry, this particular molecule, embedded value with respect to percent of intensity, you will get one peak. This peak is appeared overhead 114 only. Embedded value 114. So don't think that 114 is one of the fragment of tyrosine. Tyrosine itself, it is giving a peak at 114. So it may be a molecular impact. Sometimes it may be a directly ionic peak. Okay. Now this becomes 114. This 114 is a multiply charged ion for which one? Tyrosine. Okay. Right. So even if you take magnesium metal, it can have a tendency to lose 2 electrons during electronic impact. They won't lose 1 electron, they may lose at a time 2 electrons because it is belongs to 2A. So when magnesium loses 2 electrons, this is Mg plus 2. And if you want to calculate embedded value, normally mass of magnesium is 24 divided by 2. So finally, what is your answer? 12. So 12 means, so 12, and here in mass spectrum you will get like this. This is embedded value, percentage of intensity. Here you will get a peak at 12, embedded 12. This 12 indicates that it is belongs to which one? It is belongs to magnesium plus 2, like that. Okay. So every time don't think that whenever if you are getting embedded value of a corresponding species, they may carry unipositive charge. They may carry 2 charges, 3 charges, or multiple charges. That number will be divided by mass of corresponding molecular fragment. Finally you will get one more embedded value. So that is multiply charge ion. So after multiply charged ion, next ion is molecule, molecular ion interaction ion. So this ion responsible to give a corresponding peak. Molecule, molecular ion, interaction ion. Now this kind of ions are produced by after formation of a molecular ion collisions with a neutral molecule. So there is abstraction of hydrogen or one neutral atom is going to be taken by molecular ion from neutral, which is not going to be formed a molecular ion. Okay, so generally this kind of ions are, it is represented at m plus x. So otherwise we can say m plus 1 generally represented at m plus 1. Means almost it looks like isotopic peak only, but it is not isotopic peak. Okay, normally molecule molecular ion interactions generally appeared at some selective functional groups. After formation of a molecular ion, that molecular ion is going to interact with a neutral molecule and that will abstract the hydrogen, and that is represented in the form of m plus 1. So this all kind of ions after collision they are represented at m plus 1, similar to isotopic peak, but this is not a isotopic peak. Example for this already given. What are the examples for this? Ethers, we can go for nitriles, ethers, nitriles and nitroalkane, nitro groups, otherwise nitro functional groups. Okay, so best example, see, this is one ether. Here lone pair of electron is present. Now I am doing 70 electron volts. Initially there is a formation of a molecular ion. Loss of electron will take place here. Now this is molecular ion. I am writing second molecular ion. This is second molecular ion. Okay, two molecular ions are formed here with this. One molecule not formed two. Suppose here n number of molecules are there. Few molecules forms this same molecule collide with other molecular ion. So on that time what happens, see, this hydrogen breaks here, it will migrate from here to here. So if they migrate, this is OCH3 and it is hydrogen and here positive and here lone pair of electron, and this is removed in the term of, here this is OCH3. Remember here what you will get, a radical or not? This radical forms a double bond and here you will get plus. So initially this is a molecular ion or not? This is a molecular ion. What is embedded value of molecular ion? 36 plus 4, 40. 40 plus 6, 46. So embedded value is 46. Every carbon 12. Every oxygen also 12. Generally. But actually every oxygen 16 we need to count. But in fast I am saying, here 3 elements are there. 1, 2, 3. 36. 36 plus 4, 40. Like that you need to count so that you can get answer very fastly. Every oxygen 16, every carbon 12, but assume that every oxygen is also carbon during calculation of MZ. 1, 2, 3, 36 plus 4, 40. 40 plus 6, 46. MZ value 46. But what happens, see here, this molecule collide with neutral. This is going to collide with one more molecular ion, otherwise it may also collide with neutral. Neutral also possible. Molecule, molecular ion, remember, if you are confusing, you better you take like this. Don't think that it is going to collide with molecular ion. It may also collide with a neutral molecule, which is not going to form a molecular ion. Now this hydrogen migrate from here to here and forms a cation. This MZ value is more than 46. You will get 47 or not? Here this is 46 and this is 47. So now this is looks like a m plus 1 peak. This is looks like m plus 1 peak. So generally we are thinking about this one, but actually this molecular ion collide with a molecule. That's why molecular ion interaction peak. So this is called molecular ion interaction peak. A additional peak formed during collision establishes between molecular ion and neutral molecule. That is called molecular ion interaction peak. So this is always represented at m plus 1. But m plus 1 is not always isotopic peak. Generally m plus, whenever if word comes, that m plus number always we are going to think about isotopic peak. But that is not isotopic peak every time. It may be a molecule, molecular and interaction peak. Clear? Right. Only these functional groups are important. Which kind of functional groups will show a corresponding M+1 peak? Only isotopic peaks, nitriles, ethers, and one more they will give nitro compound. Option D, all they will give. On the time, better you select all. Even you can take a nitrile as one of the example. Here carbon, nitrogen, nitrile I am taking. This is on electronic impact. There is a formation of molecular ion. Carbon, nitrogen, triple bond, radical cation, right? Now it is going to belongs to molecular ion. Then what is M/Z value of this molecular ion? M/Z value. M/Z value of this one, see every carbon just count as 12. And every nitrogen also 12. 1, 2, 3, 36 plus 4, 40. 40 plus 3, 43. 4 or 2 you need to count? 2. 1, 2, 3, 36. 36 plus 2, 38. 38 plus this, 31. Okay. So here how much value? 46. Additionally 4. 4 will be there. But what happens? You will get only 41. Means here hydrogens are disappearing, 3 hydrogens are disappearing, 2 values are disappearing. So total 5 will be difference. Okay. So this molecule is going to collide with a neutral molecule. CH2 carbon nitrogen triple bond. This is neutral and here hydrogen. This will break up. This transfer from here to here. That nitrogen will take that hydrogen. And here it is positive value. So this is belongs to M+1 or not? M+1 means what? The 41 plus 1. 41 plus 1 is 2. That is 42. Is it a isotopic peak? No. This is not isotopic peak. So don't think that molecular ion additional if any one peak is appeared. Molecular ion additionally one peak. Don't believe it is always isotopic peak. So I am writing a nitroalkane. This is double bond and here it is O minus 1 and this is plus. The electronic impact responsible to give CH3 nitrogen double bond O, and this is lone pair and here one electron and here it is plus. Is it radical cation? Minus 1 means one extra electron, that electron I removed here. Now it is radical cation molecular ion. Now what is implicit value of this one? First we need to calculate very fastly. 1, 2, 3, 4, 48. 48 plus 2, 50. 54, 58, 61. That's why I'm saying better you practice with 12 every time. 12 into 4, 48. Then every nitrogen 2, every oxygen 4. 48 plus 2, 50. 54, 58. Then 3, 61. Implicit value 61. So after getting this 61, it is going to impact with a neutral molecule. This is neutral actually. This is minus and this is plus. This molecule, one more time I am writing here. This hydrogen migrate from here to here. So after migration you will get additionally M plus 1 peak. This is double bond and here OH, lone pair, and this is plus. So this is called M plus 1 peak. That is 62. So three major functional groups are there which will give this kind of interactions, such as ether, nitrile, one more is nitroalkane. So that is molecule, molecular and interaction ion. So that is about all possible types of ions up to molecule, molecular and interaction ion. So only two more ions are there. Negative ion, one more is metastable ion. This is negative ion. It is not so much important, we can ignore it with one statement. So during electronic impact some ions can also form negative ion. Okay, but mass spectrometry designed such a way that the negative ions cannot be identified. It can identify only positive ions only. So you will get a negative ion, but our mass spectrometry, okay, it is only resolves only positive charge species only. Negative charge species are highly impossible to determine. So negative mass spectrometry is there, but that is not include our syllabus. Okay, only I will give one statement, then I can go through directly metastable ion. Okay, so the negative charged ion, right, directly formed in mass spectrometry is negative ion. The negative charged ion formed in mass spectrometry is negative ion. Okay, so can you identify negative ions here? Negative ions are unable to isolate, unable to determine, otherwise isolate. We can't identify negative charged ion in mass spectrometry. So especially nitrogen or halogen compounds. Nitrogen or halogen compounds, N or X. Nitrogen halogen compound shows negative ion. This will show negative ion during absorption of electron by electronic impact. Here ejection will not take place here. Absorption will take place. Absorption nothing but When beam of electron is coming towards nitrogen, that nitrogen will take electron. It will suck one electron. Okay? But normally what happens? Nitrogen can lose one electron during electronic impact. Halogen may lose one electron during electronic impact. That is not takes place in negative mass spectrometry. In negative mass spectrometry, nitrogen and halogen compounds will suck one electron. That is intaking one electron. So that's why always it will liberate a negative charge which will be appeared like this. See, this is methyl and here 2 electron and here 1 hydrogen, 1 electron I am writing. This is on electronic impact, 70 electron volts. Here 1 independent electron is there or not? So this independent electron is going to take 1 electron from this electronic impact. Then nitrogen carry 2 extra electrons. 1. This electron and electronic impact. This electron, once if it is bombarded, during collision what happens? See, they never lose electron. It will take electron from this electronic impact. So once if they take electron from this electron will take 1 more electron from here and forms a negative ion. So this ion we can also write like this. This is CH3, nitrogen, -1 and here hydrogen. Like this, otherwise like this. You can write anyway. Okay? So even if you take any halogen, suppose if I take chlorine having 7 electrons in their valence shell. Electronic impact 70 electron volts, it will donate 1 electron and forms a negative ion. Okay? So sometimes what happens, see, HX, hydrochloric acid. Now electronic impact 70 electron volts, it will give directly Cl minus. Means it will break this bond. It will break this bond. Chlorine carry 1 electron. That 1 electron will take 1 more electron from electronic impact and converts into negative ion. Okay? So even from hydrocarbons also same process. Suppose CH3Cl. Now electronic impact and your molecule is Cl minus and there is a loss of CH3 radical. So what you observe every time? Breaking and converting into a corresponding negative ion. Means this lone pair of electron is not possible to remove. It is not possible to remove here. Now we are breaking over here. So this is very few, not effective number. Very few ions will form like this. That's why we can neglect negative ions here. We can focus only on positive ions because it is a separate spectra. Okay, right. So that is about negative charged ion, and this is last one in case of types of ion. Metastable ion. So generally metastable ion represented by M star. It is not molecular ion, it is metastable ion. So somewhere if they given M star, that belongs to metastable ion, not molecular ion, not a fragment ion. It is also one kind of fragment ion, but not takes place at normal fragment region of molecular ion. It may takes a different area. That is the difference. Metastable ion. First I will show a instrumentation involved in mass spectrometry. Then I will explain what is instrumentation in mass spectrometry. So rough instrumentation I am giving now. This is sample. They are heating devices. So here it is a inlet, sample inlet. This is sample inlet tube. We are entering the sample. It may be a solid or it may be a liquid. You can take any one. Solid liquid will be entered into sample handling system. This is called SHS, sample handling system. So I am sending a sample which is a solid state or liquid state. Now this is called heating devices. Heating devices. Heating devices supplement some heat energy. Now this solid and liquid is going to be converted to gas. It is a gaseous sample or vapor sample. So once if it is converted, now it is connected to one more. So this is called sample reservoir. This is called sample reservoir. So the gaseous sample which is present here, that will enter into reservoir. So here some high pressure will be maintained. Almost all 10 to the power of 4 to 10 to the power of 5 torsions. A pressure has been maintained over sample reservoir. Okay. Now once if it is enter into ionic chamber, this is called ionic chamber. Most important one. Ionic chamber is a key instrumentation over here. Okay. So this is a tungsten filament. It is a tungsten filament. Tungsten filament, and here two electrodes are present, high potential electrodes, and here positive charge poles will be there inside. This is positive charge, here also positive charge. So this is positive poles present inside of the ionic chamber. This is totally is a ionic chamber. This total is called ionic chamber. Now sample is enters over here. This is sample entry point to ionic chamber. When sample is entering over here, now this is a tungsten filament which will deliver a beam of electrons. So beam of electrons are coming like this. This is electron. Now beam of electron sample both are perpendicular to each other. Now sample is coming like this. Electrons are coming from the filament exactly perpendicular. So when this perpendicular electrons are contact with molecule, this molecule readily forms molecular ion. Okay. After formation of molecular ion, then they are further undergo fragmentation and forms a radical cation, forms a positive ion, it may forms a negative ion, it may forms a neutral, etc. Negative ion is possible, positive possible, and what is one more? It may also form neutral. Now positive poles and this positive what happens? Repulsion will take place. Now this positive pole pushes the positive charge outside of the ionic chamber. So this is 1 to 10 kilovolts of high potential electrodes. Okay, 1 to 10 kilovolts of high electrode potentials. Here potential energy is very high. So after pushing out the sample ions from the ionic chamber, remember this name, this total belongs to ionic chamber. Ionic chamber is the square size chamber in which there is a presence of a tungsten element which will give a pool of electrons. Electrons are coming from tungsten. These electrons are going to collide with a molecule. This is molecule. A group of molecules coming here from this. This is group of gaseous state molecule. They are coming like this. Every dot is nothing but M. Molecule loses one electron and forms when they collide with this. If this electron collide with this molecule, loses one electron and forms molecular ion. So same energy sufficient to break this molecular ion into further ions. You may expect a variable types of ions. That ions are called molecular ion, cation, negative ion and neutral. So we are introduced a positive poles within the ionic chamber. This positive poles will push us this positive charge, radical cation and cation, and that will be enter into this small outlet. This outlet carry two high potential electrodes are present, which is allowed to move this corresponding positive charge ions outside. Okay, they are readily entering here, and here we are connecting a U-shaped mass analyzer. Here you will expect a mass analyzer like this. This is called mass analyzer. So this mass analyzer further connected to, this is a magnetic field. Outside one field is present. Magnetic field. Okay, so I'm introducing one magnetic field in this U-chub mass analyzer. This total U-shaped instrument is called mass analyzer. So how many magnetic fields are present? Only one magnetic field. Outside how many fields are there in this U chamber? U chamber carry only one field. So when one field is present, that is called single focused mass analyzer. You remember this point. What is the meaning of single focused? Single focus nothing but when the cations which are coming out from this ionic chamber to this U-shaped chamber. This U-shaped chamber is nothing but mass analyzer. If they carry only one field, that is magnetic field, then that is called single focused. Some U-shaped chambers are there which carry two fields, magnetic and electric field. Then that is called double focus mass instrumentation or mass analyzer. Now this is further connected to a corrector. Now this corrector further connected to amplifier. Okay, so this amplifier further connected to detector. So this is detector. This detector further connected to system. Okay, so means it is further connected to computer, otherwise you can write directly a system. This is system. So once if it is connected to system, that signals are going to be converted to signals. Whatever electric signals are present, that will be converted to a intent signal in the form of ambassador value. So this is a complete mass spectrum instrumentation. So when the ions which are coming out from here, so already in ionic chamber, these ions are undergoing fragmentation or not? Molecular undergo fragmentation and giving this kind of ions or not? And these ions are coming out from the mass ionic chamber. This ionic chamber too, it is entering into mass analyzer. This is called mass analyzer. U-shaped instrument is nothing but mass analyzer. So it is a field where magnetic field is not observed. So if magnetic field is not observed, this is called field free region. Field free region. Okay, field free region. This is also represented as field free region. FFR, remember. Field free region nothing but whatever ions which are generated within the ionic chamber, they will enter over here. Now once if they enter into this mass analyzer, there is no field is present over here. Any magnetic field is not present. That is called field free region. Now it is enter into magnetic field. Now this is not a field free region. Some field is there, magnetic field. So that's why it is called field free region. This is single focus mass spectrometry. Now here, suppose if some ions are entering here now. See, this is M1 plus is entered, M2 plus is entered, M3 plus is entered, right? So once if this undergo fragmentation in ionic chamber, now this high potential electrode pushes this ion with some energy. So once if they enter over here, then this is nothing but accelerated ions. Accelerated ions having a different embedded value. Accelerated ion nothing but this high potential electrodes pushes these ions based on their mass. Once if they enter over here, so based when cation is get accelerated, they undergo some time to travel up to collector. Okay, this is called time of flight. The time taken by any accelerated ion from inlet to outlet. And if it is initiated from here to here, after crossing inlet to outlet, that is called flight down time. Okay, so it may take a long time. A ion may take a long time like this, or ion may take a less time. That is called time flight down. Or otherwise you can say flight down path. Both are same. Flight down path, otherwise time of flight. Both are same. The time taken by a cations which are produced in mass analyzer from inlet to outlet. Okay, from ionic chamber to collector. That is called time of flight. Time of flight depends upon the MZ value of a corresponding fragment. Suppose the fragment MZ value is very less, so time of flight is very less, it can reach very fastly. Suppose if MZ value of a fragment or molecular ion or any other species, if it is very high, it is a bulky species, so pushing capacity is very poor, so that's why it will take much more time to flight. So it will take much more time and it will reach at last. At last, if it is ending, means it is appeared at high mass region. Clear? So this U-shaped chamber is nothing but a mass analyzer. The time taken to travel any ion in mass analyzer is nothing but a flight down time or time of flight. Both names are same. Time of flight. So this is collector, amplifier, detector finally connected to system. This is called single focus mass instrumentation. So now still we not introduce what is metastable ion. I will explain what is metastable ion. Right now you need to remember up to sample handling system, sample reservoir. This is key point. So next I will write a diagram such a way that I will write only this U-shaped instrumentation. I will write from here to here only. I won't write this all things every time. If you want to explain any metastable ion. Okay, right. Sample handling system, SHS. Sample inlet, it may be solid or liquid, convert into gas by using these heating devices. Now it is entered into sample reservoir which is maintained by high pressure. Then this gaseous sample molecules enter into ionic chamber. So this is also called flight down path. Flight down path or time of flight, both are same. So these two statements are remain same. How much time it will spend in U chamber is called time of flight. Clear? So here you write some points. These points belongs to ionic chamber. See, The ions produced in ionic chamber are known as simple ions. Simple ions. So these ions I am saying. The ions produced in ionic chamber are known as simple ions. So positive poles in ionic chamber pushes positive ions through high potential electrodes. Pushes through high potential electrode. This is called high potential electrode. These two positive charge poles pushes these positive ions through high potential electrodes. Okay, next, positive ions get activated due to potential energy or potential due to potential of electrodes. Positive ions get activated due to potential of electrodes known as accelerated ions. This is accelerated ions. So whatever positive ions are there, they are get interacted by these high potential electrodes, so they will be get activated. Activated means speed will be get differ based on their implicit value. They are called accelerated ions. They are accelerated ions. Clear? Right, next. So the time taken by ion to travel in mass analyzer is known as time of flight. It is also called flight down time. Time of flight or flight down time, both are same. So how much time this ion is taken to travel in this mass analyzer U tube, that is called flight down time. Okay, so if mass analyzer having single field known as single focus mass spectrometry. This is called single focus mass spectrometry. If mass analyzer having only one field, that may be electric field. So this is a mass analyzer. So you focus on this two only this inlet and outlet. and here one field I am using now. This field is called magnetic field. Same structure like this. This is called single focus mass instrumentation. Single focus mass spectrometry. So single focus mass spectrometry having less resolution as compared to double focus. Separation capacity very high for double only. Suppose see some fragments having same embedded value. Some fragments having same embedded value, but molecular formula is different. On the time both having same peaks or not, they will appear at same embedded value only. So we are generally unable to identify some fragments having same embedded value, but atoms present in that particular fragment is different. They may carry one nitrogen, but they carry halogen, but embedded value remains same. On that time, this single focus mass spectrometry unable to identify such type of fragments. Means if some fragments, if some positive charged ions having same embedded value but differ in their number of atoms, number of elements and nature of elements. So but single focus mass spectrometry unable to identify the corresponding ions. So that is a drawback of single focused. So that's why we are using a high resoluted mass spectrometry, that is called double focus mass spectrometry. Double focus mass spectrometry means we are going to insert two fields. So there you can discriminate the ions which having a same embedded value but differ in their atoms. Suppose if you take any one particular element, in the two carbons, hydrogens, all are belongs to 29. Some elements are there, carbon, nitrogen and some other elements, all are belongs to 29 only. But both are same? No, but embedded value is same or not? So when embedded value is same, but fragment charge is different, on that time, this cannot be helpful. It is not going to give complete information. That's why we are going to connect one more field over here. Okay, that is nothing but double focus mass instrumentation. So then what is the difference between single focused and double focused? Double focus will give more clarity as compared to single focus regarding M plus ions with the different atoms. Carbon, oxygen, hydrogen is there, one embedded value. Carbon, hydrogen, nitrogen, same embedded value. Can you identify? No, you can't identify. You think that may carry nitrogen, may carry oxygen. There is no clarity. So on that time, single focus mass spectrometry cannot help. Only double focus mass spectrometry can help. Okay, so what is double focus mass spectrometry? So in mass analyzer, if two fields are connected, that is called double focus mass spectrometry. Right, it is same. If mass analyzer having two fields, so when they carry two fields, that is known as double focus mass spectrometry. If mass analyzer having two fields, that is known as double focus mass spectrometry. So especially for which reason it will be used here? High resolution. They having high resolution. What is the meaning of resolution? Separation. I will explain later what is resolution. But remember only one point. Separation of two ions having similar embedded value. Here it can't be separate two ions having similar embedded value. Two ions are there whose embedded value is same. Okay, so we can't separate in this one, but we can separate in this one. That is called double focus mass spectrometry. Double focus mass spectrometry having high resolution capacity as compared to single focus. You write better, high resolution. Having high resolution which can separate two ions having similar embedded value. So it would be like this, a rough diagram I am giving. It is a mass analyzer. This is electric field. This is magnetic field. So here I am using a electric field. It is first field, and see this is magnetic field. two fields are using now. Okay, so this is called this first field free region. First field free region. This point explain. Field free region. First field free region. And what about this one in between them? See, between electric field and magnetic field one gap is there. That gap is called second field free region. Second field free region. First field free region, second field free region. Like that, two fields are going to be introduced. So what is the use of these two fields? You will get more separation of ions. Time of flight will be get differ. So when time of flight is get differ, we can identify the corresponding cation very easily. Okay. So if I take a single focus mass spectrometry or instrumentation, we can't separate ions clearly. Especially the cations having same embedded value but differ in their elements. Same embedded value but elements are differ. So you will get only same line. One line you will get. But here, so two cations having a different elements, different atoms in one molecule, that can be discriminated very easily by using double focus. This is called double focus mass instrumentation. So if you want to separate clearly, if you want to get a more structural information, use double focused. Over. What is metastable ion? What is our concept? What is metastable ion? Still we not discussed. Still we not discussed what is metastable ion. What we discussed right now? Mass spectrometry instrumentation we learn. If you know mass spectrometry instrumentation, then only you can understand what is metastable ion. Okay, still we not discuss what is metastable ion. We discussed only what is molecular ion, what is instrumentation, how molecular undergo fragmentation, where it will undergo fragmentation. Okay, so here only one key point you remember, the ions produced in mass analyzer. The ions produced in mass analyzer, that is different. But right now we discussed only one point, the ions produced in ionic chamber. Okay, the ions produced in ionic chamber is nothing but a simple ions. Okay, so before connecting this, one chamber is there or not? One square chamber. In that square chamber, ions are producing. That ions are nothing but simple ions. That ions only entering into mass analyzer. The ions generated or created in ionic chamber, that ions based on embedded value, based on their acceleration, they are entering into mass analyzer. Only that point you remember. Means we are not generating any new ions in mass analyzer. Whatever positive ions are generated in ionic chamber, that ions are entering into mass analyzer. That's it. Okay. Now here, kinetic energy of a ion. Kinetic energy of an ion traveling in mass analyzer. So what is the formula? We know of mv square. This is a formula to calculate kinetic energy of ion. Here I am taking one ion. This is m1 plus M2 plus M3 plus whatever it may be, you take any one. So what is the kinetic energy of this particular ion during traveling from inlet to outlet? So that is normally taken by kinetic energy formula. Kinetic energy is equal to half mv square. Okay, and we know one more formula. Kinetic energy can be also represented by Z into V. I will explain what is ZV. Okay, kinetic energy is equal to ZV. So now if you compare these two, it is a kinetic energy of ion, it is also called kinetic energy of corresponding ion. So I can make relation between these two. ZV is equal to half mv square or not? Half mv square. If I write these two over here, 2ZV by m is equal to V. And if I write square, you will get this one. So can I write direct formula? V is equal to 2ZV by m. So what is this V and what is this m? So what is this V here? Velocity of ion. This small v indicates velocity of ion. What about Z? Charge on ion. Charge present on ion. And what about this V, capital V, this V? This is potential of electrode. How much potential we are using, that will be given here. Potential of electrode. Okay, and finally what about M here? Mass of ion. So if you know this, we can calculate velocity. Speed we can calculate if you know this all. Okay, so what is Z indicates? Charge present on that ion. It may be unipositive, dipositive, tripositive, etc. And here what is this? Potential of electrode. Means there I use 1 to 10 kilovolts of high potential electrodes or not. That will be given here. Then this is mass of ion, velocity of ion can be calculated. If you want to calculate velocity, we required charge on ion, mass of ion. Then what is one more? High electrode potential. Based on that, I can calculate speed. So if you calculate speed, can you calculate time of flight or not? Yes. So this is a formula you need to remember. How to calculate velocity in mass spectrometry? By using ZV by m, 2ZV by m under root. Okay, so you can, if you square both sides, if you square it and if you remove this, if you write this 2 over here, 2ZV is equal to mv square. Square on both sides. 2 and root will be get cancelled. You will get root 2ZV by m, and this will be velocity. So velocity is equal to 2ZV by m. And if you want to calculate any unknown ion, so this is a formula for, we don't know the ion, unknown ion MZ value. Unknown ion MZ value is equals to, we can calculate like this, B square R square by 2V. This is one more formula to calculate MZ. What is MZ? Mass by charge ratio. We can also calculate by using B square R square by 2ZV. So what about B? B is equal to magnetic field used in mass analyzer. What is the magnetic field used in mass analyzer? What about AR here? Radius of time of flight ion. Okay, what will be the radius of time of flight ion? Okay, then what about V? Potential of electrodes. Potential of electrodes. This is the variable symbols required to calculate MZ value and velocity in mass spectrum. These two formulas you need to remember. Only two formulas are there. Kinetic energy of any traveling ion in mass analyzer is equal to half mv square. So this half mv square is equal to its corresponding charge, and this kinetic energy depends on these two, product of these two. What is it? Charge of ion, V is equal to potential of electrode. If you make these two product, that will give this kinetic energy. Means indirectly this speed equal to these two, product of this. Okay, kinetic energy of any ion in mass analyzer is equal to charge present on that ion and potential of electrode, both. Now this and this both are same, and if you square it and if you cancel the two charges, roots and number, then you will get V is equal to 2ZV by m. So velocity can be calculated by using this formula. M by Z will be calculated by using this formula. If you know the magnetic field and if you know the time of flight radius, and if you know the potential of electrode, then finally we can calculate implicit value. Magnetic field used in mass analyzer. How much magnetic field we are using? Radius of time of flight. Time of flight and finally potential of electrodes. Clear? Now see this. So this is a mass analyzer. Now I am defining what is a metastable ion and try to identify the difference between metastable ion and simple ion. Okay, so this is the inlet where ions are coming from ionic chamber. Some ions are coming. Suppose let us say the ion is M1. M1 is an ion whose charge is M plus. Okay, so generally here 8 kilovolts of energy is required to accelerate this ion from 1 to 10 potential electrodes. High potential electrodes we are using or not in ionic chamber. So that is nearly 8 kilovolts of energy is required to accelerate this ion. So when this ion is coming, initially where it is initiated? Where this ion is initiated? It is initiated in an ionic chamber. Now, whenever if any ion enter into mass analyzer, after entering into mass analyzer, they undergo further fragmentation. This is M2 plus and this is M3 neutral I am saying. M3 neutral. Okay. Now, this ion is called metastable ion. Now, this is the key difference between these two. Metastable ion whose acceleration capacity is less than parent ion. Now, this is 6 kilovolts of energy and this one will share 2 kilovolts of energy. Okay. So, can you define what is a metastable ion? Can you define what is a metastable ion based on the explanation which I given just now? The newly generated ion in mass analyzer from a corresponding ion already generated in ionic chamber. See, is this ion generated in ionic chamber? No. This is not generated in ionic chamber. It is generated in mass analyzer. If any ion generates in mass analyzer, that is called metastable ion. Okay, this ion cannot be generated in ionic chamber. Okay, so in mass analyzer, it is generally represented by daughter. This is daughter. And what about this one? Parent. Daughter square by parent is represented by m star. That is a general representation of a metastable ion. I will show how to represent a metastable ion, but right now remember only one key point. Metastable ion is an ion produced in mass analyzer from a corresponding ion already generated in ionic chamber. Suppose if this M2 generates in ionic chamber, M1 plus or not? See, this M1 plus accelerated by 8 kilovolts of energy by potential of electrodes. So they want to travel. Whenever if it is traveling in first field free region, whenever if it is initiated, whenever if it is traveled, they undergo further fragmentation. So when they undergo further fragmentation, these volts will be distributed between these two. So here, what is the acceleration capacity? 8 kilovolts here. But what about this one? 6 kilovolts. So now whether parent and daughter, which can flight very fastly? Parent can fly very fast. Because here acceleration capacity very high. But what about here? Acceleration is very poor. So they can move very fastly, they can move very slowly. Acceleration is very poor. Here acceleration is very high. Suppose if it is not undergo fragmentation, I am saying. If it is not undergo fragmentation, speed is very high. Suppose if they undergo fragmentation, this will disappear. And if they disappear, it will give one positive and one neutral. This is neutral, I am saying. Neutral can identify in mass spectrometry? No, we can ignore this one. Which means M-based value of parent always greater than daughter. M-based value of parent always greater than daughter. Parent acceleration capacity greater than daughter. Because parent acceleration somewhat distributed to daughter, remaining part will be distributed to one more daughter, but this daughter can't be identified. So that's why always remember, parent acceleration or fast will ability of running in mass analyzer is very high as compared to daughter. Okay, so your statement is this one. First you complete this, then I will give that statement. Is it clear what is metastable ion? It is very important in CSR examination. What is metastable ion? Simple ion is different, metastable ion is different. Okay, right. First you take this. The positive charged ion generated in mass analyzer generally this is known as metastable ion. The positive charged ion generated in mass analyzer is known as metastable ion. Metastable ion, it is represented by m star is equal to m2 square by m1. M star is equal to m2 square by m1. Okay. So what is m star? Metastable ion, this one. Metastable ion is equal to, what about m2? This is daughter. Daughter square by what? Parent M-based value. Parent. Mass of daughter by mass of parent. Daughter square by parent. So that will give one mass. That mass is called apparent mass. Here m star is equal to what? M star is a apparent mass of metastable ion. It is not clear mass. M star is a apparent mass of metastable ion. Apparent mass of metastable ion. It is represented by m star is equal to m2 square by m1, daughter square by parent. Here m star is, don't write directly m by z value. M star nothing but m by z value or apparent mass of metastable ion. So who is metastable ion? Either m2 or m1. m2 only, not m1. Daughter is a metastable ion. So here we are writing a apparent mass. Apparent mass always less than calculated. Here whatever data we are writing and that value whatever you are writing, that value will be little bit 0.1 to 0.4 value will be less. So don't write this value exactly same. Okay, after doing calculations, what I am saying is, suppose here this is a parent. Parents are having m by z value. Daughter having some m by z value or not? Suppose if it is 91, 65. Coming from 91 or not? Okay, so what I am saying is, if parent and daughter and this is parent, if both are given and whose m by z value if you substitute here and if you calculate, if you divide daughter m by z value square by parent m by z value, you will get one value. That is a apparent m by z value. That is not real. Means some value will be less than expected. Suppose if you are getting, if you divide these two, if you are getting exactly rough calculations on your paper, you will get 49. But that will be 48.70, 48.90, like that you will get. Means your calculated and observed will be slightly differ. That's why it is called apparent mass. Apparent mass means it is not a real mass, slightly differ. So why it is get differ? Due to the neutral ion formation or neutral fragment formation. Slight amount will be reduced here. So slight m by z value will be get reduced from daughter. That's why you will not get exact value. So if they given m star, say metastable ion m by z value. Otherwise metastable ion apparent m by z value. Okay, they won't mention m by z value every time for metastable ion. They will mention apparent m by z value of a metastable ion. What is apparent m by z value? Apparent m by z value means it is an m by z value of a metastable ion only, but it is slight less than calculated. So we are calculated and we are getting exactly suppose 60. We are calculated and we are getting 60. But here you will get only 59.70, 59.80, 90, but you will not get exact number. So 0.1 to 0.5 difference will be there. That's why that is called apparent. So you will not get real value. Okay, your key point is this one. In mass spectrum, metastable ion liberates non-integer, low intense, broad diffuse peak. Broad diffused peak. It is very easy to identify metastable ion. Most of the cases you will get non-integer. It is not always non-integer. You will get fraction, but that is not always fraction. And your intensity is very less. Peak is not sharp. Peak is diffused. You will get a broad peak. You will not get a sharp lines like that. So in mass spectrometry, I represented every time with a short lines, right? But especially in mass spectrometry for metastable ion, intensity of metastable ion is very poor. Intensity height will be very poor. You will not get a intense ion. Height will be very less. And very, very important thing is, it is always represented by a broad diffused peak. Broad diffused peak, nothing but this one. You will get like this. See, this is percentage of intensity, m by z value. Now, this is a broad diffused peak. When you get a broad diffused peak in mass spectrometry, definitely some ions are generated in a mass analyzer. Okay, so here they will write one line, and here I am writing one more line. So most commonly, this may be parent. This is parent and this is daughter. Parent and daughter. So this is daughter or not? What about this parent? M1 plus. And what about this? M2 plus. So between M1 and M2, in middle, if you calculate this data, there you will get an intense peak here. That becomes, this is a metastable ion. This metastable ion produced from this parent ion. That is the meaning. So you can write a m by z value of a daughter. Like this one line we can write. And we can write parent ion like this, one more line. But you will get one diffuse in between them. So don't think that we need to start from parent and we need to end this daughter, this diffusion. This diffusion never start with parent. This diffusion never end with daughter. That depends upon the fragments. Because see, between M1 and M2, if some more ions are coming, we are writing this m by z value over here only. So don't write this line from here to here every time. Don't touch that line from parent to daughter every time. Sometimes what happens, parent is M1 only. Remember, parent is M1. So some other peaks are appeared now. Okay? So some other peaks are appeared, but here parent is there. Who is parent? M1. M1 plus is a parent. Like this, peak will be appeared. So if you divide this value square by this value, you will get one number, right? That number will be over here. Okay? Then you can say this will be a metastable ion. Try to understand. So when you get a broad peak in mass spectrometry, like this, if any broad peak is coming, means definitely one of the peak will be metastable ion. So this is a metastable ion peak intensity. This is apparent mass of a metastable ion. But real m by z value of daughter is this one, parent is this one. Clear? Right. So here this is key points. This you may expect in your examination. Metastable ion liberates with a non-integer value, low intensity. Intensity is very less or not? M star, this is M star. This is M star, it is daughter and this is parent. M star, daughter, parent. Okay? This is always a low intense. It is not a sharp line. See, these are, all are sharp lines or not? But here this becomes a broad line. So I can say it is a broad diffused peak. It will be diffused. So that is about types of ions. Types of ions are over in mass spectrometry. Total 9 types of ions we discussed, starting from molecular ion, fragment ion, odd electron ion, even electron ion, later on isotopic ion, multiply charged ion, molecular ion, interaction ion, then followed by negative ion, finally metastable ion. In metastable ion we also discuss mass instrumentation, single focus mass spectrometry, double focus mass spectrometry, finally metastable ion. What is metastable ion? So the newly generated positively charged ion in mass analyzer. Here key point is don't forget to write mass analyzer. If you not mention the word mass analyzer, that statement is wrong. Already one ion generated in a mass ionic chamber. Ion already generated in a mass ionic chamber. That ion forcefully enter into mass analyzer. Due to high potential electrode, accelerated ion further undergo fragmentation. When accelerated ion further undergo fragmentation, so this acceleration capacity will be distributed to the two species equally or unequally. But whichever is a positive ion, that positive ion is nothing but a metastable ion. Suppose if this fragment undergo fragmentation, if you are getting a neutral, that is not metastable ion. Definitely you need to get at least one positive ion. Positive enters from ionic chamber to mass analyzer. One positive charge is enter from ionic chamber to mass analyzer. They undergo further fragmentation in mass analyzer. It may be single focused or double focused. Now, if it is undergo fragmentation, if they give one positive ion, then only this ion is said to be metastable ion. Now, between parent and daughter, which is a metastable ion? In interviews they will ask, which is metastable ion? Metastable ion is daughter only, not parent. Okay, this because it is a newly generated or not? It is not newly generated. This is the one which is newly generated, whose embedded value and parent embedded value we are writing in the form of m star. M star is nothing but a apparent mass. It is not a real mass. Apparent mass is nothing but the mass whose value will be little bit less than expected. Means here if you add this embedded value square by this embedded value over here in this formula. You remember this formula. How to calculate apparent mass of metastable ion? Daughter square by parent embedded value. Then you will get one value. That value is not accurate value you will get. Calculated value, observed value, little bit different. That is called apparent. Yet apparent means don't think that much effectively. You can even ignore also. Nothing will happen. But sometimes in examination, what is apparent mass of given cation in mass analyzer they will ask. Apparent mass nothing but slightly differ in their calculated mass. That's it. So remember this. These points are very important for metastable ion. Always metastable ion will give low intensity. It is a broad diffused peak. It is comes from parent and daughter. If you know who is parent, who is daughter, based on this symbol we can confirm that one fragment ion is generated in a mass analyzer chamber, not in ionic chamber. This is called mass analyzer chamber. Left side is called ionic chamber. Okay. So that is end of types of ions. So few questions we will discuss in next class regarding all types of ions. Then I will start what is types of ions and what are mass spectra rules. Okay. We'll stop here. Right. You can leave now. So tomorrow schedule will be announced in your WhatsApp group. Okay. That will be confirmed in your regular class schedule. Okay. We'll stop here.